Thank you for joining us for today's HDL seminar. Nice full rooms, new faces, some old, so that's great to have. Today it is my pleasure to introduce our speaker, Chanel Cabak. Chanel is currently a master's student in biomedical engineering here at the University of Calgary, specializing in computational neuroscience. She completed her Bachelor of Science in Exercise and Health Physiology in 2025, also from here at the University of Calgary in the Faculty of Kinesiology, where she first got involved in research. She was working on a topic that actually has contributed substantially to the research that she will be presenting today in her talk. Her current research now focuses on enhancing concussion and mild traumatic brain injury rehabilitation through electrical vestibular stimulation and AI-based gait and balance assessments. She is co-supervised by Dr. Ryan Peters and Dr. Jeremy Wong. And outside of the lab, Chanel has an impressive athletic background. So she was a high-performance competitive figure skater for much of her life, and now she's into marathon running. She's preparing for her full marathon later this year, and will also be taking on a high rocks competition, which I asked was kind of a mix of everything. It's a new thing. So I asked her more about that later. But another fun fact about Chanel is that she's ambidextrous and red-green colorblind, so do not get in a car with her, especially at night.
Yeah, just at night.
Today she will be presenting her work titled A Low-Cost Markerless Motion Capture System to Automate Functional Gait Assessment. Thank you, Chanel.
Thank you. All right, so I guess we'll get started now. So for those of you that don't know me, my name is Chanel. And today I'm going to talk about my project, which is called a low-cost markerless motion capture system to automate functional gait assessment. So to start off with just a bit of background information on who I am, as I'm sure majority of you probably have absolutely no idea. So I grew up as a high-performance competitive figure skater for a majority of my life. I moved away from home at a very young age. I was very thankful for all the opportunities my parents gave me to be able to move away from home at a young age. So I trained at the highest level, competing both nationally and internationally in my sport. And this was kind of who I was for the first 20 years of my life. I then moved to Calgary in 2019, initially for figure skating, and then they had a really cool kines program, so I of course had to join that. And then I did my Bachelor of Science in Exercise and Health Physiology, and I just graduated last spring in 2025, and then started my Master's here in Biomedical Engineering in September. And as Ashna said, I'm now an avid marathon runner, so you will see me out on the trails at 4 a.m. or actually probably most of you won't see me out there at that time because most people are not awake at that hour. And as Ryan would probably say that I'm addicted to running, but I don't think that's a bad thing, so it's pretty fun. So kind of why I decided to go into the realm of research that I do was because of my background in figure skating. Combining the biomechanics as well as the vestibular system. So it was kind of.
Sorry.
No, it's okay. Okay, perfect. So looking at the biomechanics that goes into executing a perfect triple Lutz like this one here, and then also the vestibular adaptation that happens from many, many hours of spinning on the ice. Like this level 4 change combination spin. I don't know if I could actually still do this right now, but at a time, yes. So this was kind of where my interest lied, and then now I'm able to integrate this into a master's project, which is pretty cool. So for my master's, I'll just briefly touch on this as this isn't really the focus of the talk, but for my master's, I'll be looking at enhancing concussion and mild traumatic brain injury rehabilitation through electrical vestibular stimulation and AI-driven gait and balance assessments. So I'll kind of talk a bit about those AI-driven gait assessments today, so you'll get a bit of background information on that. And then also getting to do a little side passion project on the vestibular system during repetitive spinning that happens with elite figure skaters, and kind of their sensitivity to the electrical vestibular stimulation and how they compare against non-trained skaters. So now getting into the actual reason why I'm here to talk today. So falls are an injury risk at any given time, especially more frequently if you are a competitive figure skater like myself. For me, my phone is filled with many countless outtakes of very painful falls, like this one right here. This one really hurt the ego, but that's okay. So as an athlete, this area of research is truly of interest to me because I understand the importance of precise movement analysis and injury prevention. Throughout my career, I have had many painful falls. Here's another one. Maybe a little dramatic on that one, but that's okay. And this one really hurts. I still have trauma from that one. And then also, because I am a runner, I have to include a little track one. So these highlight the true beauty of sports. Now, assessing functional mobility is critical, but it's very difficult to do. Gait assessments are important to do because of fall risk. So falls lead all-cause of injury in adults aged 65 years and older, with roughly 24,000 people being hospitalized each year with fall-related hip fractures, as well as our aging population. We know that 85 plus is the fastest growing age group and is expected to triple by the year 2046. So this is a really important population to target. But what predicts functional mobility? Well, walking speed is actually as predictive as blood pressure and can be known as a sixth vital sign, as well as step width. So we know that older adults prefer a more wider stance. And with functional gait assessment, we see that fall risk is associated with step width. So getting into what a functional gait assessment, or FGA, actually is. So it's a 10-item clinical gait test that is designed to evaluate an individual's ability to maintain stability while walking under a range of conditions. Now, these conditions increasingly get more challenging as the test goes on. So FGA in older adults has traditionally required manual in-person quantification of clinical measures such as walking speed and step placement. Now, this reliance on individuals trained in motion analysis hinders the frequency with which they are performed and reduces their generalizability and replicability. So as I said, it consists of 10 different walking tasks. So you start with essentially a baseline gait test where you tell someone to walk from one point to another, which is 20 feet long. And then there's different tasks such as changes in gait speed, head turns, walking backwards, walking with their eyes closed, and even up the stairs. So they're walking along a 20-foot long walkway, and it's 12 inches wide. And essentially for each task, they are scored from 3 to 0. So 3 would indicate a normal score, 2 would be a mild impairment, 1 would be a moderate impairment, and then 0 would be a severe impairment. And essentially 22 out of 30 is the cutoff score. So anyone scoring below that threshold would be at an increased risk for falls. So if we look at FGA, one of the issues with it is the subjective scoring. So it's very clinician dependent. For each task, they're having to monitor different things. So they're looking at gait speed, they're tracking the lateral step placement, as well as evaluating balance and task performance. So if we take a look at that first task of the FGA, which is the normal condition, also known as gait level surface, for this, essentially, you're told to walk from here to the next mark, and a normal score would be given for that if you're able to walk there in under 5.5 seconds with no assistive devices, good speed, no evidence of imbalance, normal gait pattern, and deviates no more than 6 inches from the 12-inch width walkway. So we can see there's really no quantitative thresholds with these measurements. What necessarily does significant or minor speed change mean? So we can see here's a little example of Osman doing the walking over the obstacle. So for this, a normal score would be given if he's able to walk over the obstacle without changing speed. But how easy is it to see a change in speed with just the visual eye? So they would compare this task to the initial first one to see if there is a change in speed. So looking at the approaches that are used to look at gait assessments, now we know that traditionally marker-based motion capture has been known as the gold standard. Now these systems are very accurate, but they come with significant limitations. They're very expensive, they require complex setups with the markers and the multiple cameras, and are time consuming to run and analyze. Anyone who has done marker tracking knows just how time consuming they can be. Looking at Monica. Because yeah, there have been times where I have been sitting at my desk wanting to pull up my hair with the tracking. So because of this, they are largely confined to large-based environments. So while they give us high quality data, they're not necessarily scalable to a clinical environment. So that's where markerless motion capture comes in. It's low cost, it doesn't require markers, and can be deployed in a clinically realistic manner, using very simple and cheap camera setups. So importantly, it allows us to automatically extract clinically relevant gait metrics rather than relying on manual observation. So here you can see an example of a participant walking with our pose estimation overlay, capturing joint positions in real time, illustrating just how this approach bridges the gap between lab-grade accuracy and real-world clinical applicability. So getting into kind of the main idea behind our paper, our question became, how can we automate functional gait assessment in a clinically realistic way? So our goal for this project and the purpose was to deploy recently developed open source markerless motion capture system with custom analysis software for functional gait assessment. So our pipeline was this. We started with video data. So this came from 3 cameras, very simple setup, which I'll go over a bit later. Then we used pose estimation to essentially reconstruct movement and extract the clinically relevant gait metrics, such as step length, step width, and speed. We then applied our framework across 2 different experiments. So we started with a validation experiment, which was validating our markerless motion capture system against the traditional marker-based system. And then we applied this to the functional gait assessment within our older adults. So I'll dive into experiment 1 here, which was our validation. So for this, we had 3 participants, and this is showing our 3 camera setup here along the long axis. So it was a 6-meter long walkway, and we used face space for the marker-based motion capture, and then the free mocap project for our markerless motion capture. And essentially our goal here was to determine the validity of the markerless motion capture system to compute step length, step width, and walking speed. Now these 3 measures are necessary and sufficient to automate functional gait assessment. So to determine the accuracy of computer vision methods, we used marker-based motion capture, the face space, and we collected 6 different markers per participant. So we collected from the feet, the torso, and the head. Then we used the free mocap project to measure body segment position combined with custom code for FGA analysis. Now, free mocap represents one of the first among a set of open source 3D computer vision projects capable of integrating pose estimation from multiple cameras into estimated segment locations with consumer-grade cameras. So we recorded walking trials of 4-meter distances with both systems under 2 different conditions. So condition 1 was just a normal preferred gait width. And then we also did a wide condition where we had participants place their feet along the 0.3 meter marked walkway. We then performed 3 replications of each condition, and to spatially align the 2 systems, we subtracted the initial position, so the time 0 of each left foot, to register the 2 systems at the beginning of the walking bout. So going into our results from our first experiment, we found that markerless motion capture was accurate in its detection of foot placements. So if we look here at figure A here on the top, we can see here, we time aligned our two systems by determining the maximum cross correlation of the anterior posterior foot speed, also known as just the forward walking speed. So we have time on the x-axis there and then the foot speed on the y. Then for B here, so this is looking at bout extraction. So for each trial, we cross-correlated the summation of each system's markerless and marker-based left and right foot speed, and then computed the maximum value of the cross-correlation. Then C here is looking at footfall detection. So to detect the left and the right stance periods, foot speed was low pass filtered at 3 Hertz, and then the regions where foot speed was below a threshold of 0.5 meters per second was identified as the stance phase. So the average position of the stance region was taken as the footstep location, also known as the mid-stance instant, which is from a Carlisle and Co. paper. And then here in D, we're looking at head speed, which was another variable we wanted to look at. So we measured head speed as a time derivative of the forward position of the head marker, which was located centrally on the back of the head via a headband. And then for the markerless system, we define it as a time derivative of the average forward position of the left and the right ear and the nose key points. And then down here are on the right hand side, E and F. So this is just looking at step length and width vectors that were computed based on the mid-stance instances as well of consecutive steps. So here are a few more figures from our first experiment. So on A here, these are just individual walking bouts that are comparing our markerless system with our marker-based system. So you can see that they are very well aligned there. And then looking at B here, the scatter plot. So we have step length here and step width here. For step length, we had a R squared of 0.98. And then for step width, an R squared of 0.97, indicating extremely high accuracy. So these plots show very strong correlation between the markerless and the marker-based systems. However, correlation alone does not imply agreement. So that's why we also performed a blend-Altman test. So we can see on this side, we have the blend-Altman for step length and then step width down below as well. And we can see no significant bias here, meaning our system is not just correlated, but it is clinically reliable. So getting into our experiment number 2 here, which was the functional gait assessment performed with the older adults. So for this, we had 5 participants with a mean age of 69 years old, and we got them all to complete a full functional gait assessment with each task being repeated 3 times. Now, all older adults were living independently at the time of the experiment and completed the experiment only after informed consent had been given and they felt comfortable performing all of the given tasks. So kind of what we wanted to get out of this project was eliminating that subjective scoring with FGA. So we came up with these thresholds. So for all of the different conditions, scoring relies on these qualitative judgments made by an observer, which renders test outcomes susceptible to observer bias. So for example, we'll go back to that condition 1, which is the gait level surface. So for this requires the clinician to continuously monitor the maximum lateral foot placement outside of that 12-inch width walkway, while determining whether the speed is good, slower, or shows evidence of imbalance, but there's not necessarily a quantification of each adjective. So using the outputs of our system, we automated the functional gait scoring by setting thresholds for FGA categories on gait speed relative to that gait level surface condition. So changes in gait speed of 0.1 to 0.2 meters per second may be important across multiple patient groups, and based on the measured average speed of our FGA condition 1 of our experiment, a 0.1 to 0.2 meter per second change in gait speed corresponded to approximately 5 to 10% change. Now, this formed the basis of our threshold approach, and we have used 75% to 125% change in gait speed for FGA scoring, where essentially that 100% corresponds to the speed that they walked at during condition 1. Note, however, that these threshold categorizations are meant to demonstrate that the automation approach and parameters in the algorithm that may be edited to best suit the needs of a clinician. So these would be different depending on the population group. So getting into the results from our experiment here, this one on the top is just showing all the step placements across all 10 of the different conditions. And then on the bottom here, we're looking at head speed for all of the 10 conditions as well. So for the head speed trajectories, they were sufficient to show the deviations in walking speed, forward speed per the condition, relative to that normal preferred walking in the condition number 1. Then these are just showing on the top here the average FGA scores. They were very similar to previous literature values that we have seen in the older cohorts of ages 70 to 79 and 80 to 89. And most subjects scored lower on that backwards trial, which you can see here, which is as to be expected. Now, functional gait assessment scores for all subjects here are ordered in ascending order. And data for mean age subject groups was adapted by a Walker 2007 paper, which determined age reference norms for performance on the FGA in older adults. Now, for the ages 70 to 79 and 80 and 89. So 70, 79 is in the squares there, and then 80, 89 is the triangles. So then on the bottom here in this figure, we're looking at fluctuations in the maximum lateral step placement, which is a big thing that they monitor in the FGA. So step width magnitude is thought to reflect control of the lateral stability, given that instability of human gait in the frontal plane. So step length varies with walking speed, and gait speed decreases with age. Now, finally, this figure, this isn't necessarily telling us anything new other than Stu here walks really wide. So in the blue, that's pretty much mostly what you can take away from this. But these are just proposed additional measures of maximum and mean step width and movement duration, which is applicable to all trials along the limits for scoring, which is shown in the horizontal lines here, which you can kind of see. So these are just generalized measures. This shows we're not restricted to only what FGA actually measures, and generalized tests can extend beyond the FGA. So we can measure other variables such as step width in all of the 10 different conditions, which we see here. So kind of the 4 main takeaways of this paper was, first, feasibility. This approach is very feasible. We show that a low-cost, relatively simple, AI-driven motion capture system can be used to perform functional gait assessment in a way that really aligns with existing clinical workflows, as well as free mocap. So our markerless system aligned very well with the gold standard. So we were able to reliably capture step placement with very strong agreement for step width and step length. As well as it's affordable. The whole camera setup costs less than $200, which is about 1 to 10% the cost of a traditional marker-based setup. So this makes this really clinically realistic, as well as it's meaningful. This approach is by automating the functional gait assessment scoring, we reduce subjectivity and introduce additional objective metrics like step width and continuous gait speed that aren't captured through standard observation. However, of course, all studies come with limitations, and ours was not without them. So to start off, our small sample size. The scope of this project was to use the automated gait analysis of the Markerless data to systematize functional gait assessments with accurate foot placement and gait speed. Now, the FGA is a very comprehensive test with multiple dependent measures across all 10 conditions. So therefore, statistically significant differences across individuals and conditions with appropriate control for type 1 error rates was beyond the scope of this study. Essentially, this shows that it's proof of principle that clinically relevant gait metrics can be automatically extracted with limited clinician intervention. Now, future work involving larger cohorts and patient populations will be required to determine whether these automated measures reliably track changes in gait behavior over time to predict fall risk and support interventions. As well as our camera calibration requirement, now future studies may seek to simplify this or provide streamlined hardware that eliminates it entirely. Now, the current system does take some time and training to perform, so if calibration fails or if errors are large, the calibration then must be repeated. Now, the software does provide a number of detected calibration boards and pixel reprojection errors, which in practice does provide useful feedback. And we found that detecting about 400 calibration boards provided accurate measures. As well as if a clinic allows the cameras to be applied on a fixed surface and they're not touched or moved, then a calibration may only need to be done once, which would essentially eliminate the continuous calibration. Clothing sensitivity was another one of our limitations. So the degree to which clothing affects the performance of markerless motion capture is still an open-ended question and likely depends on the dependent measures. So in our experience, we found that using shoes that contrast with the ground color, as well as clothing that contrasts with the background, had the best results and can substantially improve tracking performance. So for clinical applications, we would recommend performing a brief pilot trial prior to the data collection, after which participants can be provided with contrasting garments if necessary to ensure reliable tracking and a systematic approach to clothing effects with respect to gait and step placement is one of the potential future extensions of this study. So just to conclude, this work shows that a low-cost markerless system can essentially achieve accuracy very comparable to our gold standard marker-based motion capture, however, in a clinically realistic setting. And ultimately, this moves gait assessment from subjective observation towards something that is objective, accessible, and very scalable. And with that, I just want to thank my co-authors on this paper, Osman and Jeremy, and also Ryan for volunteering me for seminar. I always love a chance to talk. So with that, I'll take questions now. Thanks, Ryan.
Floor is open for questions. Who would like to start? Olive.
Thanks for the talk. I'm super curious to know what happens if someone does score below that threshold of breakthrough or whatever on the test or the follow-up.
I'm not fully sure on what the follow-up is, just that then they're at more risk for falls. So I think it's more common for older adults to be scoring below that. And then I think maybe that would be a point where, oh, we send you to physio or something in that regard, just because they are at an increased risk. So maybe even if we're noticing like with the first few conditions of the FGA, because the tasks are increasingly getting more challenging, if we saw someone was like really struggling on just even like the head turns, we wouldn't have them like walk backwards or walk with their eyes closed or upstairs. So yeah.
Quick follow-up to that too. Do you expect your system to be characterizing more people as having higher risk for falls, or do you expect it to be the other way, where it's kind of characterizing less people? This is compared to like the clinical assessment.
Yeah, I think it would be able to categorize more people because like with the FGA, clinicians are just looking at like lateral step deviation, but with our quantitative measures, like if you're looking at step width, we can see actual like real measures of how much they deviate other than just with the naked eye. So I think we'd be able to maybe classify that a bit more, especially with the thresholds. I feel like it's a better approach to that.
I have a question kind of along the same lines.
Yes.
Where did you compare your scores from like a subjective clinician assessment to your automated
Well,
one?
we looked like that one figure I had was showing like literature values of kind of the same age groups, and those were just clinician dependent scores.
Yeah, but you didn't have some clinician like
No.
score the same participants?
No, we were just scoring them like with our naked eye as well. So like if we saw someone was like, for example, like with the backwards walking, they would deviate quite a lot. So because in the clinician functional gait assessment definition, they have like if you deviate more than 6 inches from that 12-inch width walkway, then it becomes a lower score. So we were scoring them ourselves, but we didn't have a clinician.
Other questions from the audience? Micah.
Thanks for your talk. I'm curious, so is the goal of this at the end of the day to do fall risk classification for like a specific patient or subject?
That isn't necessarily our goal. However, I think that could be implemented in a clinic if that's what they were using it for. Like, for example, for my master's, I'll be kind of using this in a concussion-based population. So not necessarily looking at fall risk. However, we know like if they are scoring below that threshold, then they are at increased risk for falls, but that's not like the main goal of it for us. Makes sense. Yeah.
So then follow-up question is, I guess for this application, then you were looking at kind of the metrics that are related to increase or like worse FGA score in older results. Correct? Did you categorize like, or maybe follow up these participants to see like whether the predicted score from your algorithms actually resulted in like higher fall risk or that like later on in the?
We haven't followed up with any of our participants, no. They were all like pretty healthy older adults, so none of them like scored below this threshold per se. So we didn't feel it was like necessary in that regard. But I think in like future applications, like this could be applied in a clinic where they have someone come in, like a disease population, for example, and they're looking and they do a baseline FGA where they're getting these thresholds, and then they could look at them if they're receiving treatment and then do a follow-up FGA and see if this making a difference, I think. So it could be used in that sense for sure.
Last question.
Yeah.
How do you think, sorry, your pipeline would change when you're looking at like different gait conditions or, you know, for example, someone that has Parkinson's versus peripheral neuropathy? How would you envision your pipeline changing or adapting?
I think it's the core framework of this is very generalizable. However, it can be adapted with the different populations. As I said, this was kind of just like a threshold that we set where we saw, but it can be adapted for different populations. Like for Parkinson's, for example, you would probably make those thresholds wider. And then if you're looking at a healthy young adult population, they'd probably be like smaller thresholds for sure. So I think it is able to be adapted for sure, depending on the population.
Okay, while we're reading for others, one more question from me. Have you talked to any clinicians and showed them the stuff, and is there any feedback on like whether they prefer to stick with the traditional measures or do they like where this could go in the future?
Yeah, that's kind of where my master's work will be centered on, so maybe I'll come back next year and do a talk on that and answer your questions.
Okay, any other questions from the audience for Chanel? Yes. Nick, go ahead.
Who is doing the functional gait assessments? What clinicians and what clinics and where do they do it and who do they plan to?
Quite a lot of clinics use it. It's one of the most widely used gait assessment tests. So actually we have clinics here at U of C that use it. A lot of physiotherapists will do this to evaluate gait in different groups. Yeah. Does that answer your question?
Well, I can see the relevance in people my age.
Yeah.
Pretty sure we're not doing it to young people or athletes downstairs in the clinic that I'm involved with.
No, I don't think it would be necessary in, like, obviously in younger, healthy populations. However, like for the older adults, it is useful because it is able.
What I'm getting at is a lot of these things are done in people that are already injured.
Yeah.
So how applicable is this in the normal population? What are the values that are available in the normal population to allow us to understand what's going on when you see somebody, or more importantly, to be able to prevent one of these things from happening, because it's a big deal, as you said.
Yeah, falls are extremely important to prevent. So I think like all the older adults we looked at were all healthy. So I think in the case of that, if you're doing it in healthy older adults, and then you see something in the gait assessment where they are then scoring below that threshold, then I think there's reason to be concerned then. So then maybe even they are sent to physio or something, but they might not necessarily have an injury, or then they just have to be more careful about kind of, you know, taking their walking a little bit slow. We had actually a husband and wife who were like competing with each other, trying to like walk faster than the other, and then we're like, no, slow down, don't want to fall. But so I think it's could be applied to instances like that.
Brent, and then Walter had a question, and then Doctor.
Do you know how clinicians take mobility aids and things like that into a score like this?
So with the normal score, it says without the use of assistive devices. So then they would just automatically not be able to receive that normal score. So they would automatically fall to a 2 or lower, yeah.
And Walter, you have a question?
Sure, yeah. So, thanks for the talk. You mentioned that step length, step width, and walking speed was necessary and sufficient condition for what? I wasn't really sure what is necessary and sufficient.
Like to automate the functional gait assessment with the Markerless system.
And the other thing that I was curious about is some of the step width parameters. You showed deviations of up to half a meter,
Yeah,
which seem
with the eyes closed and the backwards, it's pretty easy to deviate that much. Just because then obviously your vision, without your vision, you don't really know where you are in space as well. So we did see like quite a bit of deviation in those conditions.
so. How was step width measured? Was that from like within one step, like from left to right, or was that over the 6
Yeah.
distance or so that you took the most to the left and the most to the right? And step width was defined as, like over a series of steps, or was it from step to step?
From step to step, I believe, but you can look at it over the whole range as well. Yeah.
Just a big number, surprised me a little bit there, half a meter, but I guess blind.
Yeah, when you're going backwards, for sure, it's pretty easy. Even like we did a lot of trials like ourselves, like walking with our eyes closed, and we'd close our eyes and then we'd get to the end and realize we're like all the way over here, and we're like, what? So it's pretty easy to deviate that much with your eyes closed, but yeah.
So do you somehow normalize that to leg lengths? If I have an angular deviation of
Yeah,
5 degrees and I have long legs, that will give me a bigger step
that's true, yeah.
than a smaller person. You normalize that?
That's not something we did do, as we only had 5 people, so. But I think that's something that could be applied in the future for sure, and something to kind of look out for, yeah.
The other thing that I was wondering is the step length, step width, and walking speed. I would assume that walking speed and step length are highly correlated.
Yeah.
And therefore, they're not really independent parameters that you measure.
Yeah. I would say they're pretty similar for sure. They're a bit different, but yeah, I'm not fully sure.
I just wondered if you only would need the one and then you're
Yeah,
almost giving
maybe
the other
just, even if we just looked at like step width, step length, and then just head speed even, as opposed to walking speed. But yeah.
The other thing I didn't quite understand, you say this is AI driven. I wasn't sure where the AI is in your approach.
Yeah, so these algorithms are designed like by us. So it's very I guess, machine learning heavy in that regard. And then basically we work with these computers to be able to put these pose estimation right on top of the skeleton, and it automates the skeleton, so.
There are two neural networks, one detects people.
Jeremy can comment more on this.
Yeah, one neural network detects people, and the other neural network detects where the segment poses are. And then we have to do some math to combine that information from different cameras to the 3D estimation. The AI part is getting humans from pictures and getting a body pose once you identify where the human.
But you have the camera, you still have the cameras.
Yeah.
Why not have an algorithm that just measures where your foot stops and, where the landing is, and just get.
Do you have a single camera or multiple cameras, or how would you?
You said you had
There's 3 cameras, yeah.
So like this multiple camera is the setup that Janelle was talking about.
Yeah. I'm not sure what you.
I just mean in the camera that would see where one foot is where the other one is, and I should be able to somehow measure from toe to toe. Fairly accurately. I'm not quite sure where
I think you're saying, yeah, so we do an extrinsic calibration, which figures out where the cameras are, and then you can guess, once you have pictures, you can guess where the food are. You can use the estimated positions of the cameras in their locations to guess where you just have to store, you're doing something like a regression. You have to store those numbers somewhere, and that's what we do. But it's convenient, just convenient to have an AI grab the people. I think that's the AI part, which is maybe where we're talking across each other. All that's convenient is just to establishing where the person is without having to label any images.
But you still need to do a calibration.
Yeah, so we do like an extrinsic and intrinsic calibration of the cameras.
And then you mentioned high accuracy, so like, what is the accuracy that you would consider sufficient for step widths, step length, speed?
Like in what regard?
Well, that's what I'm asking you. You said accuracy. I'm asking, how do you define high accuracy in step lengths? If I know that my step length is 90 centimeters, is 95 centimeters?
Well, I think if we're looking at how, like, we compared it with the marker-based system, and pretty much the steps were aligning identical. So I think that's where the high accuracy is coming from in that regard. And then even like we did like a wide trial with the markers and saw that the widths are very comparable between the two systems. So I think that's where the accuracy comes from, as marker-based is the gold standard. So if it's aligning well with that system, I consider that pretty highly accurate, I guess.
Most important question. This is a muscle mechanics question.
Oh boy.
You were a figure skater.
Yep. You can ask me about spins or jumps.
Yeah, exactly, that's what I'm going to do.
Okay.
And so in order to jump up and twirl 3 times,
Yeah.
you must have a good height.
Yeah. I think my vertical is pretty good.
Exactly. So you must have quite a lot of power, which would suggest that you are more fast twitch fibers since you're an international athlete.
Yep. And now I'm doing long distance running.
You're doing something that seems completely again, like a sprinter trying to run a marathon.
Yeah. I don't know, you can retrain I don't know, it's fun. I like what you can change your fiber types, right? To a degree.
Well, you can make, I always say in my class, you can make a fast fiber much more oxidative.
Yes, yeah.
And so you can train oxidative capacity even if you're full.
So I think if I'm training like 7 days a week running long distances, those fibers become different. I think if I were to try and go to a triple Lutz right now, it probably wouldn't go well, but.
In my exam question for people will ask.
See, I'm not in your class, so.
Was a world-class figure skater, ever be a world-class marathon runner?
Yeah, what would they say?
What would you say?
Yes, you would be able to. Is that no? Wow.
Oh.
You're destroying my marathon hopes and dreams.
Let us know your results.
Okay.
Stick it to
You're
I'm
right.
gonna qualify for Boston and just,
I'm talking real fast.
yeah, okay.
2 hours.
Yeah, no, I know. Oh, I don't think I would be able to get that fast, for sure not, no. Oh, thanks, Penny.
Vic, we had a question back there?
Oh, yeah, okay, first question is about the step, speed. Is it a standard to measure step speed in the functional gait? I know in my lab we use a metronome for them to
Yeah.
test the flows, because otherwise it seems fairly subjective to the population, like if you're testing an elite athlete,
Yeah.
in my experience, like walk as fast as possible.
Mhm,
Even if you say walk at your normal pace. So was a metronome used for your gait?
Yeah, the metronome's used for the head, like rotations, I guess, so that it's like a 2 hertz, with the head. And then also because this is applied to the older adults, for like, for example, for that condition 1, they have to get from point A to point B in the span of 5.5 seconds. Like, it doesn't say if they're quicker than that, it's just before that 5.5 seconds is kind of the cutoff. Obviously, yeah, if you did have athletes doing this, they would be much quicker, for sure.
And then the second question, like completely unrelated,
Mhm.
but sort of filled off with some of the other questions. You talked about like just the goals of it overall and like applying it to different populations.
Mhm.
Do you see like potential for it to be able to, like, instead of like do they fit the standard, like could you see it being used for populations that we don't, like, that might be hard to categorize their specific functional gaits, like spastic CP, where it's hard to like actually see the movements or
Yeah,
feel it as
for
something?
sure. I think
Yeah.
like,
Like
sorry,
being able to describe it better for populations that we don't know a lot about.
I think for sure, even in like a population like CP, I think using like marker-based motion capture on them is much more challenging. So in the cases of this markerless system, I think with that, it's much more easier for them and they might be more inclined to do a gait assessment this way. Yeah, especially in like kids with CP, for example, for sure.
Benno, you had a question? And then back.
Let's assume I come to you,
Mhm.
I'm old enough. You assess me,
Yeah,
get a certain result
uh-huh,
that shows some problems, some
okay,
of the variables.
yeah,
Now, these problems may be due to some brain functions,
they could be.
it may be some muscle sleep functions.
Mhm.
What do you do with me?
Send you on your way. I'm just kidding. In that case, I'd probably refer you to like a physio or even, maybe go see your doctor and say you did this specific gait test and you found out you were at more of an increased risk for falls. And then I think in that regard, a clinician could be really helpful in kind of figuring out what to do as next steps to maybe eliminate that fall risk.
Does your testing help you to maybe make sure that I go to a neuro specialist?
Yeah.
Or that I go to a muscle sleep specialist? Or?
I'm not sure if necessarily there's a way for us to tell fully what the underlying condition would be.
You cannot use the data for that.
Yeah, it could be used potentially for that. Yeah, I'm not.
It could be or it could not.
It could be.
So what concrete?
Sorry,
What concrete would you say that?
like why?
Which variable?
I think step width is probably the most important one I'd go with.
That more brain rate, or is that more muscle sleep related?
Maybe more brain.
Why?
Oh, I don't know fully. I guess like If we're thinking of like Parkinson's, for example, like they have more of a slower shuffle gait, so we would see different changes with that, with FGA, where they're walking slower, probably their width is a bit different, even the length of their steps. So I think that could be classified, obviously, as neurological. But then I guess there's also musculoskeletal underlying with that as well. So.
Well, that's a good question, actually.
Yeah. Let's keep going.
Now, I'm just throwing
Yeah.
out something, so. For example, I have somebody walk along a straight way and
Yeah,
then they have a relatively tight step width or multiple steps, and then all of a sudden they have a big step. That might be something different than somebody who has
Yeah.
consistently wide steps.
yeah,
So maybe the variation, for example, somebody that has consistently wide steps might not feel strong enough and
True.
might be more a mechanical problem, so they
uh-huh,
walk wide to be always
yeah,
secure.
which is why we see with the older adults, they have a more wider
Whereas
stance.
somebody else might have, not so much a mechanical problem, but maybe some brain, some sensation problem. Might have a few fairly good steps, and then all of a sudden, they might have a big step. So I wonder if in the variation of step lengths and step widths, there might be something hidden that maybe Dr. Nig is
Yeah,
trying to find.
that is true. That could be a future measure we look at for sure.
I think with their master's data set,
Yeah.
they're looking at concussion.
Concussion, yeah.
Minor traumatic brain injuries.
Mhm.
You're probably, once you have that data, come back to this one and
Yeah.
try to compare.
I'll be back in a
versus
year.
that.
Yeah,
It seems like, yeah, from both the questions and also from thinking about it, it seems like there could be some things, but currently your model, it may not be able to.
Yeah, yeah. Currently, I don't have a definitive answer on that. Yeah.
Okay, other questions for
No.
Chanel?
Just a quick follow-up. I see that at all, that some people have, consistently wide steps and then other ones
Yeah, I
are
think,
very much more, they have a tight steps and then a wide one, and so
Mhm.
do you see those type of variations?
yeah, for sure. I think even like what you were getting at about like the leg length, even like if you take a larger person, they are gonna walk wider as opposed to a smaller person. So definitely there are changes that come down to just the physiology of a person as well. So, yeah, for sure.
Chanel, in clinics we know and we have other ways to detect risk of fall. Are you planning to, for example, balance test?
Yep.
The stand?
Yep.
This.
That's gonna be my master's. Yeah.
So, because there is a lot of information in the balance test.
Yeah,
example,
for sure.
There is some ways to qualify this difference between muscle and skeletal vestibular system,
Yeah.
sensor and motor
Yeah.
system.
Yeah.
So I think it will be interesting to see how the
Yeah,
the
for
system
sure.
performs.
Yeah, kind of like I said, this is like a very small part that's gonna be included within my master's, so that's something I'll definitely be looking at is those balance assessments combined with the gait tests, with the electrical vestibular stimulation. So we'll definitely be able to look at more variables with the combination of all that.
So I follow up that, so are you thinking to use all this data combined to kind of predict, to build a model? Like,
Yeah,
okay.
yeah, that would be definitely a pathway that we'd be looking to go down for sure.
Okay, any last questions for Chanel?
With your masters, do you see that this can be paired with the scat 5, scat 6? Because I know
Yeah.
like baseline testing for that, it could be a lot of times that's like, well, the worst I do at the baseline, I'm gonna be pretty good when if I do get concussed. They know that's not right, but at the end of the day, your best commodity is your availability in sports. So like this be a way of evaluating the severity of concussion and like
Yep.
progressing or seeing if someone's suitable to return to sport.
Yeah.
That is better detectable compared to just recall.
Yeah, essentially, I will be using the post-concussion symptom scale in the SCAT-6 within my masters. So that's how we will evaluate symptom severity. Then they will do this baseline gait test, balance test, and then they'll receive the electrical vestibular stimulation. And we'll see how this affects essentially the concussion. So the PCSS, like the post-concussion symptom scale, will be performed before they do the baseline gait and balance, like kind of early on in their concussion, and then they'll have this intervention period with the EVS, and then we'll do the symptom scale as well after. So we're hoping that with the combination of the gait assessments, balance assessments, EVS, that hopefully they can return to school, sport, work all quicker. So that's kind of, yeah, the main goal of the masters.
And then are you working with, is that Dr. Matani? Yeah. Are you like, I'm not sure if he's a football or not, but are you guys planning on working with like U Sports?
With like Catherine Schneider, like the concussion injury month, yeah. Yeah. It's the plan.
Okay, with that, let's thank Chanel for her talk.